everybody. So today we're going to be talking about exponential growth and decay, and this is the last new material that we will cover going towards exam 4 as well as the final exam. So what this section does, it takes the last section we talked about on compound interest and looks at one of those four formulas in particular, the PERT formula. Now it gives it a few different stylistic notations. Sometimes it'll use A's in this A subscript 0 or N subscript 0, but it's all still just the PERT formula, just they're using different notation where A is the final amount, P is the initial amount, E is still just E, the number, R is the rate, and T is time. So keep that in mind. And then here, this A sub 0 or N sub 0, that's the initial amount. K is what they use to refer to the rate. T is time. In this section, time doesn't have to be in years though. And we'll see that for these problems I'll go over. So the first example I have in the notes, something about strontium 90, whatever that is. It's a name of some mineral, and it decays according to some formula here. So this is the PERT formula. So A sub 0 here is the initial amount. A over here is the final amount. E is just E. This is the rate, and that's the time. So it still correlates with what we know before about the PERT formula. And then assume that there's a scientist that has 400 grams to start off with. And they first ask about the decay rate. Now the decay rate, this should be pretty simple because they give that, as long as we know how to dissect this formula, the decay rate we can identify as coming from this quantity. So that quantity is in fact negative 0.0244, but they want the rate, and the rate refers to a percentage. So they simply want you to convert this value into a percentage, and that will be more explicit by the percent sign on this problem. So this would be negative 2.44%. And this is the answer that they would want for part A. For part B, they want to know how much of this mineral is left after 20 years. So this is when we're going to start plugging in values. So we have a few unknowns from the introduction of the problem. The final amount, the initial amount, we know the rate already, and the time. So we want to plug in as many of these as possible. Well, it turns out we know the starting amount. In fact, they kind of shoved that idea in here on the last sentence of the problem statement. So if anything, we know that the initial amount is 400, and that is a constant value. In fact, I could take this formula, replace that A subscript 0 that I just erased with 400, because it tells us exactly what the initial amount is. So if anything, we have that, so it's either down to what the final amount is or the time. You might notice in part B, they give us 20 years. So that sounds like a pretty good time right there. So we can go ahead and plug in 400 e raised to the negative 0.0244. And I'm following this formula directly with the t representing 20. And really, this is just a calculator problem. You notice I still keep the exponent in parentheses. I think that's just good practice to make sure you put it in your calculator correctly. But we did this in the last section. 400, you need to remember where the e is on your calculator. Negative 0.0244 times 20, and then you can close your parenthesis. And I get, so it does say round to the nearest whole number. And you will notice a lot of these problems, some will say whole number to the 10th, nearest 10th or 100th, or one decimal place. This one says the nearest whole number. That seems to be 246 is what I get for this problem. part C, it now asks when will 300 grams be left. So one indication here is that when we are looking for when, that implies we're looking for time. And they give us the final value. So we're taking the formula before, but now instead of having a t value and solving for a, we're going to plug in 300 for the final value. So 300 for the final value, and we're going to solve for t. And so it gives us a format like this, which should be fairly similar to what we did in the previous section when we found t in those few problems from the homework. And what we did in those problems is we first divided by 400 so we can get the exponential part by itself. Remember, 400 is not part of this exponential. So we first divide both sides by 400. And 300 divided by 400, it simplifies nicely, that's just 0.75. And then from here, the variable is stuck in the exponent, which means we have to apply a natural log. And that makes more sense because now we've gotten the exponential part by itself. So we apply the natural log simply by starting with the notation. So just like this. And notice how the ln and the e are right next to each other with no other interference, so they cancel each other out. And what we get from here is now we get natural log of 0.75 is equal to, well, whatever that exponent remains as. So just like this. Finally, to get t by itself, we simply have to divide by, well, the negative 0.0244. And the problem does ask for us to round to the nearest tenth, which means we're going to go ahead, throw all of this in the calculator, and see what we get. 0.0244, and I set to the nearest tenth, I get 11.8. So to conclude example 1, we are now going to look for the half-life of this mineral. And if you see the word half-life, we've seen something like this before, except instead of half-life, it said double. If a certain value doubles, except in this case, instead of double, the starting value is going to be split in half. So what is the initial value in this problem? Seems like that was the 400 here. So what half-life is referring to it means that the final amount, or the capital A in this case, is equal to, well, half is 1/2 times the starting value, which was 400. That's simply 200. So now it wants us to do the exact same problem as before in part C, but instead of when will 300 grams remain, it's simply when will 200 grams remain. So it's the exact same problem, except instead of 300, it's 200. And I will go ahead and work it out the same. And you will see quite a few problems that do mention half-life, so this is something to keep in mind. So we're going to, just like we did in part C, divide both sides by 400. and we will get 0.5. Again, just like what we did in the previous part, we can apply the natural log. And I'm skipping a few steps because this follows the exact same lines of steps as the previous problem does. And again, we've put it in the calculator. In fact, you can go up to your previous entry in the calculator if you want and change 0.75 to just 0.5. And I get 28.4. And this will satisfy the round to the nearest 10th condition that they ask. But other than that, that does conclude example 1. For the last problem that we looked at, we got fortunate because it gave us the rate already. It was the negative 0.0244. But for the problems moving forward, well, these problems will not give us the rate, and as an intermediate step, we will need to figure out the rate before we move on with the problem. So what I did was, as I mentioned, all of the problems in this section rely on the PERT formula. Sometimes they look a little bit different. They'll use A's or N's, but ultimately it's still of this form. And if we extract it down to this form that we're used to, then you can always figure out the rate using this formula here. It's natural log of the final amount divided by the initial amount, all of that divided by whatever the time is. And again, in this section, time does not have to be in years. And I also mentioned, do not round the rate, because you could throw all of that in your calculator and get a decimal. I wouldn't recommend, and even the answer choices say this as well, do not round until you get to the final part. Since this is an intermediate step, as we'll see for this problem, if you round too early, you might end up losing precision in your final answer. So my rule of thumb is go ahead and leave this in its exact form and round once you get to the very end of the problem. So I'll go ahead and explain what that means, say in example 2 from the notes. So population of a city follows, it says exponential law. All that means is that the population follows this formula. And it does start off by saying, let n be the population, t is time, express n as a function of t. So it says it wants you to write down the PERT formula, but write it down in a specific, aesthetically pleasing way. And so I did have that written down before, and that formula, so if you go back earlier in the video, you will recognize this form. And I know to use this form instead of the form with the A, because it tells me use n. And I also have this formula in the notes. And that's all you have to do for the first part of this example. So this would be the first part. But ultimately, just keep in mind that this is still A is equal to PERT. It's still the PERT formula. It's just aesthetically different looking. And then if the population doubled over 27 months and some more information. So what I want everyone to notice is that this would be a problem where the rate is not quite given yet. So let's start with everything before the comma here. If the population doubled, okay, that means you have a starting amount, and then you multiply it by 2 to get your final amount. The current population is 20,000. Okay, so 20,000 is the initial amount. Double that would be the final amount. That's 40,000. 27 months, that's time. So now we figured out A, we figured out P, and we figured out T. So what remains, we need to figure out R. And this is where that intermediate step comes into play. It's intermediate because this doesn't answer the question, but it's going to help us answer the question. So we need to figure out what R is, the rate, and that's partially why I gave the formula here. It says it's the natural log of the final amount divided by the initial amount. So if anything, the initial amount is 20,000, that would go in the denominator. Since the population doubles, that means we go up to 40,000, just twice of 20,000, and divide all of that by whatever the time is. And as I mentioned, the time doesn't have to be in years. I'm gonna put the time in months. So 27, just simply write down 27. And as I mentioned, do not put this as a decimal because this is not the answer for part B, but this will help us. Because notice what we did was we used all the given information up until the comma, but there's more stuff after this. So this is step 1 for this problem. Step 2 is going to be, what will the population be 3 years from now? So we know the initial amount, we found the rate, and it's asking for what the population will be 3 years from now. So we know all of these values, and we have to figure out A. So this is just a calculator-based problem. So here's the exponential form. We know that P is 20,000. E is just E. The R here is all of this. Yeah, it looks very messy, but that is all part of the rate. And we can go ahead and divide 40,000 divided by 20,000 because that is a nice number. That's just ln of 2. Doubled. That gives us another key instance. So that's ln of 2. In fact, I'll write that down here just in case. So you can simplify as much as you can as long as you get exact answers. So it's still divided by 27. And that times t. Now what's interesting about this problem, and this comes up once or twice as well in the homework. So notice this says 3 years. And you might think, okay, well, let's plug in 3 for t. Well, that's a problem. Because when we figured out the rate, we used 27 for time, and 27 is in months. See, now, we can use whatever we want for time, but if we pick 1 unit, we have to be consistent. Here we pick 27 for 27 months. That means we need to convert 3 years to, well, months. And so 12 months in a year, 3 years, that's 36. So I'm putting 36 here. That's how many months, well, how many months are in 3 years. So we converted 3 years into months. But once you figure all of that out, notice all you have to do is just plug all of this in your calculator. So 20,000 e raised to b, and again, by having the parentheses set out exactly like this, if you follow all the parentheses I have here, then, so open parenthesis, put the 2, close parenthesis, divided by 27 times 36, close parenthesis. As long as you follow all of these, then order of operations will be done for you, and you should get, it does say round to the nearest whole number, so you will get, looks like 50,397. Let's make sure that that is the correct answer. Yes, so that would be part B. For part C, we're looking for how long until the population reaches 100,000 people. And notice it says how long, which implies we're looking for time. And it does give us a final value. So let's go ahead and think about what we have. We have the final value, we're looking for time. So this is still the same problem, example 2. So the rate is the natural log of 2 divided by 27, and the initial amount is still 20,000. So let's go ahead and write down all of our givens here. So the final amount is 100,000. So following this formula right here, the 100,000, the 20,000 was the starting value. E is just E, all of that raised to the natural log of 2 divided by, was it 27 or 37? 27. And then times time. So now we've plugged in everything we know. The two constants, the final value that it gave us, and now we're looking for time, i.e. how long. So again, this works out just like problem 1 did. We divide both sides by 20,000 to get the exponential part by itself. And after dividing both sides by 20,000, 100,000 divided by 20,000, that's just 5. And again, just like the last problem, we apply the natural log to both sides, which once we apply the natural log to the right-hand side, the natural log and the e cancel. And we get this, or you can put in a multiplication sign in between the number and the t if you'd like. So from here, what I like to do, I see a fraction, so I'm going to go ahead and multiply both sides by the least common denominator. So now that is 27 natural log of 5 is equal to the natural log of 2 times t. And keep in mind, the 27 does not multiply the 5 in the parentheses. 27 is multiplying the natural log of 5. This is considered to be one number by itself, one entity. It's not ln times 5. So it's all one continuous thing. But once we get over here, so again, 27 does not multiply the 5. All we have to do to get t by itself is divide by natural log of 2. And so once we do that, we get exactly this value, which now we can throw all of that in the calculator and see what we get. 27 natural log of 5, close parentheses, divided by natural log of 2, close that parenthesis, and I get 62.7. We do want to round to the nearest tenth, so that would yield 62.7. And that would conclude part C here. For example 3, we see a familiar idea. It's the half-life, and it does tell us that the half-life is 6 days. So let's go ahead and just extract that before we look at anything else. So the half-life, I mentioned this before, means that the final amount, so whatever the final amount is 1/2 of the original amount. Now, reading through this whole problem, you might notice they don't give us a quantitative final amount or an initial amount. They don't tell you that it starts off with 10 grams and that would imply that the half-life would be 5 grams. It does not give you a starting amount. You can still work the problem though, because, so in the last half-life problem we looked at, they gave us actual values to work with. But it turns out that the values themselves don't matter, because when we look at A is equal to P e raised to the RT, so the only formula we care about in this section, whenever we're solving for time, as the how long value here represents, or even when we're solving for the rate, the first thing we always do is divide both sides by p. And that again is apparent in this quotient right here. So if we think about a divided by p, well, I just said that a is 1/2 of p divided by p itself, and you get 1/2. So all of this is an elongated way of saying, well, really generalizing, if you do not have an initial or final amount, and they ask you to find the half-life, then what that generalizes to is that the quotient of a over p is simply 0.5. Because imagine if you're starting off with 100 grams or something and your final amount is 50 grams, 50 divided by 100, well, it's 0.5. If instead it was 1,500, 500 divided by 1,000 is 0.5. So again, the values don't matter, it's the quotient that matters. And you will keep getting this no matter what, which is very helpful because in all of these situations, we do end up looking at the quotient. So that's something to keep in mind when they don't actually give you a quantitative initial amount to work with. You don't always need one. And so you might look on to see that it does say 11%. And you might think, okay, 11%, well, is that the rate? Because that is a percentage. However, the answer is no. This does not represent the rate. What this represents is it's going to represent how the final amount and the initial amount compare with each other. Very similar to how this quotient reduced down to 0.5. So let's go ahead and just work out what I mean. We'll go ahead and work out everything up to the first sentence or two. Yeah, the first sentence. So it says that the half-life is 6 days, and if you're given what the half-life is, then you can figure out the rate in the same way we've done before. So remember, this is the intermediate step. The 11% is not the rate. It will be the new comparison between A and P, which we'll get to in a second. So the half-life here, we can figure out the rate. So the rate, as I have written down over here, is exactly this. But remember, A divided by P, because this is half-life, this tells us that this is the natural log of 0.5. Because A divided by P is just 1/2. And all of this is divided by whatever the time of the half-life is, which is 6 days. So we'll put 6. And although this is not the answer for the problem, this is an intermediate step that we will definitely utilize going forward. So now, that's us utilizing the half-life part of this problem. This is where the half-life comes into play. And from now, we move on to the next sentence. And it says something about 11% of this isotope remains. So this 11% comes into play. So it's saying from the initial amount to the final amount, what you're going to have remaining is 0.11, or 11%. That's how the final amount and the initial amount compare to each other. So it could have said when 50% remains. If 50% remains, then that's, well, the half-life. And we did the exact same thing over here. And so once you figure out this, if you look at the PERT formula and realize A and P, you don't know the values explicitly, but if you divided P on both sides, you would get 0.11 is equal to E raised to the rate, which we found over here, divided by 6 times time. And it does make sense that we're looking for time because it does ask for how long. Until 11% is left over. But once you get that horrendous setup, so I do admit it is an elaborate way of setting up the problem, but once you do set it up, then all you have to do is apply the steps we've done before. We take the natural log, we multiply, we divide accordingly. So here, you would take the natural log, just like we've done in the previous problems. And remember, when you take the natural log of the right-hand side, the natural log and the e cancel out, which is why we get down to here. Again, we multiply both sides by 6, which is clearing out the denominator. So that's 6, natural log of 0.11, or 0.11, it's the same thing, is equal to natural log of 0.5 t, or times t. Divide both sides to get t by itself. And let's go ahead and put this in the calculator to see what we get. And I'm pretty sure it asked for us to round to the nearest tenth. And if so, that is 19.1. And that seems good for example 3. So now we move on to example 4, where it's some amount, I think they call it compound A, and they give a bunch of extra words that we don't care about. But to, I guess, kind of extract everything and bring it down to the necessary information, there's some initial amount that goes from 0.4 to 0.36 in 30 minutes. And so we can use that information alone to determine the rate, since the rate of decay, and this is decay because we go from a larger amount to a smaller amount, we can use that to help us determine the rate first. Remember, this is an intermediate step. So let's go ahead and do that first before we even look at the problem in particular. So remember, the rate is found by the natural log of the final amount divided by the initial amount, and all of that divided by whatever the amount of time is. Well, we do have a final and initial amount that we can use. That will be, the final amount is the 0.36, and the initial amount is the 0.40, and all of that will be divided by t, and we'll go ahead and use 30. And I'll go ahead and clean this up because 0.36 divided by 0.40 is 0.9. So I did say not to round. We can simplify though, as long as we have nice answers. So 0.9 is a nice finite answer. So if anything, we have the rate, and that will help us solve, well, the question, and actually the next question after this one. So how much will remain after 3 hours? So they give us some quantity of time. We're looking for the final amount. So if anything, we start off with 0.4, 0.40, e raised to the rate and the time. The rate we just found to be natural log of 0.9, all of that divided by 30. And so we're going to multiply this by the time. Now we've seen an example of this already. We're not going to use 3. We're not plugging in 3 for time, because we used, over here we used 30 minutes. So that means our unit of time has to be in minutes. So how many minutes are in 3 hours? That's going to be 180 minutes. So that's the value we use here instead. But once you determine that, it's just a matter of plugging everything in your calculator and going from there. So 0.40, e raised to the, it does the parentheses for you, natural log of 0.9, close parentheses, divided by 30, times 180, close that parenthesis. And I'm pretty sure it wants 2 decimal places. So it wants 2 decimal places. I think it might say the nearest hundredth. So 0.21 is what I get for the first part. So the second part of this problem wants to know how long does it take for the 0.40 to reduce down to 0.10. So how long implies we're looking for time. So what we do is set up all of our givens. The final amount is 0.10. And that is equal to, and again, we're just following the PERT formula, the initial amount being the 0.40. We still have E, and the rate that we found in the previous part was natural log of 0.9 divided by 30. And the time is unknown. That's what we're looking for at the moment. So now we get here, and again, we have to solve using the ways we've been using in the previous problems, dividing both sides by 0.40 and going from there. And that should give us 0.25 is equal to e raised to the natural log of 0.9 divided by 30 times t. Again, we apply the natural log to get rid of the e here, as we've done before. And now we can multiply both sides by 30. Finally, just divide both sides by natural log of 0.9 and we get t by itself. And we'll go ahead and put all of this in the calculator. Looks like we need 1 decimal place, so let's go ahead and solve for that. I said 1 decimal place, it looks like 394.7. And that looks good. So that would conclude example 4. So the last example in the homework, it's something called a logistic model. And I'm not too sure why this problem is on the homework. I was told to keep it on here. I'm not going to focus too much on what it is or have you memorize stuff about it, so just follow what I do for this problem. I don't think it's going to show up on the test. If it does, I'll definitely elaborate more on this type of problem. Rather than that, just try to get the points for this one. So it starts off by, so this is a logistic model. There is an exponential function in the denominator, and what it starts off by asking is simply plug in 0 for t. So plug in 0 for the t all the way over here. And whenever you do that, so that's going to be a straight calculator problem. And I would recommend putting parentheses around the denominator. So it's plugging in 0 for the t here. So it is definitely a very elongated problem, but at least for part A, it does resort down to calculator work. Again, don't forget your parenthesis when you plug in the denominator. 0.8 e raised to the 0.1556 times 0, close parenthesis. And it does want you to round to 1 decimal place. So I get 88.9. So that would be part A. Part B, it says, again, why I don't think this problem should be on the homework. It says graph using a graphing utility. Now I know a lot of you use Desmos or some equivalent one like that. For the graph, I'm just going to tell you what it looks like. Again, don't focus too much on this problem. So it'll start off up here and kind of level out like this. So whatever shape, it's gonna be multiple choice, it'll be whatever one takes on this shape. And so we'll move on to part C. In part C, if you notice in the notes, what percentage of households did not own a personal computer in 1995? Now, if you notice, when the problem starts off, the logistic model, blah, 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 since 1987. So it starts off in 1987, it's saying how many do not own one in 1995. So your time here is going to be the difference between 1995 and 1987. So it's asking for that difference. So over here it was the starting amount for how many did not own a computer in 1987, and then it says fast forward 8 years. And then from there it's just a matter of plugging in that 8 as if it were the 0 over here. So it's the same type of problem, it's just plugging in 8 instead of 0. So notice I'm putting the 8 all the way over here instead of the 0. And if you know how to in your calculator, you can just go up to when you put all this in the calculator and just replace the 0 with an 8. And again, it wants you to round to 1 decimal place. What I seem to get is 82.6 for part C. So finally, we move on to part D. And what part D wants you to find, in what year will the percentage, something, 25%. In other words, they want you to plug in 25 for P and solve for T. Now this is not a fun problem. And again, I don't want you to focus too hard on this problem, so just please follow the steps that I'm doing. So as I mentioned, the 25 will go over here on the left. Everything else carries over from the given function. So the first thing you would want to do is, well, multiply out the denominator and also divide by 25. So you multiply this on both sides, and then you divide the 25, so you can get this part by itself, but then you subtract 1, this 1 on both sides. Now you're here. And so we really have no choice but to simplify this. 91.7229 divided by 25, all of that minus 1. And I get 2.668916. Again, it's not a fun problem, so just try to follow with what I'm doing. This does fit the exponential form though, provided we divide both sides by the number in front to get the exponent by itself. From here, we take the natural log of both sides to get rid of the e. finally, we have one more step, which is dividing the 0.1556 on both sides. From there, you can put all of this in the calculator. Natural log of 2.668916 divided by 0.0318, close parentheses, all of that divided by 0.1556, and I get 28 point, well, I guess technically 5. However, this is not the answer, because the problem says in what year. So this is not the year that it's referring to. This would say it's the year 28. So how you have to apply that is, remember the starting year was 1987. For your problem, it might be different. I've seen 1984, I've seen other years used. You would have to add that number to the year. And so what we have, so the 1987 plus the 28.5 and so what we're actually going to do, I guess technically this was 28.4 and it goes on and on. I rounded too quickly, so it would have screwed up this answer. But you do get 2015. Again, it's not a fun problem. You might even get lucky and be able to guess the year. But other than that, just try to follow these steps for part D, and that would conclude this section.